Okay, let's have a look at this problem now. We want to find the sum of first n terms of a geometric progression. So let's say we have a geometric progression. The general form we write it ar square, so on up to its nth term as ar to the power n minus 1. Now we want to add all of this and we want to find what is the sum. So let us denote this sum by Sn, that is the sum of first n terms of a geometric progression. Now how do we find it? There is a small little trick here. Let's say this is our equation 1. So what we can observe here is that if you multiply each term with r, then every term just converts itself to its next term. What I mean to say is, if you multiply a with r, this becomes ar, that is, it becomes the second term. If you multiply the second term with r, it becomes ar square, that is, it becomes third term. If you multiply ar square with r, it becomes ar cube, and so on. So what we could do is, we could multiply this sequence with r and then subtract it. So when we subtract it, the corresponding terms gets cancelled out. Let's have a look what I'm trying to say. So we multiply this equation by r. So on the left hand side we will have r times Sn. And now let's just try to write the equation but shift it by one term. So if you multiply this by r, what will the first term be? Ar. So we write the first term here, ar, underneath the second term. Similarly, the second term would be ar square, right? And the third term would be ar cube, and so on. Now what happens is n minus 1th term, which would normally be ar to the power n minus 2, that becomes ar to the power n minus 1, and the nth term that we have here is, if you multiply this by r, then this becomes r to the power n minus 1 plus 1, so this becomes ar to the power n. So this becomes our equation 2. Just to recap what we did, this was our original geometric progression which we were interested in. We want to find its sum. So what we just did is, we multiplied this equation with the common ratio r. So on the left side we have r to the r Sn, and now on the right side what we did is, we just shifted the term by one term. So the first term ar, we just write it below the second term here. So we have ar here, and then this the second term will become ar square, so we have ar square here, and so on. So in the end, towards the end of the sequence, what happens is, your nth term ar to the power n minus 1, if you multiply this by r, it becomes ar to the power n. Whereas the n minus 1th term, which was originally ar to the power n minus 2, it becomes ar to the power n minus 1. So this is a beautiful little trick that you can use. Now what we do is, we just subtract these two equations. So when we subtract, the sign gets changed. You have plus, it gets minus. So here it gets minus, it gets minus, minus, and so on. You have minus here, minus here. Now the beauty of this trick is that when you do this term gets cancelled. Since this is ar minus ar, it will be 0. Ar square minus ar square, this term gets cancelled. Similarly, you would have ar cube here, so this term gets cancelled. And this nth term, which you had ar to the power n minus 1, you have again here as ar to the power n minus 1, but with a minus sign. So this thing gets cancelled out. So in the end, what you are left here is, on the left hand side you have Sn times 1 minus r, that is Sn minus r Sn, so Sn minus Sn times 1 minus r, and on the right hand side you have a left here. So a minus 0 will be a, and the only term that will be left is this last term here. So a minus a r to the power n. Therefore from here you can write the expression of Sn as, if you take a common here, so Sn as a multiplied by 1 minus r to the power n divided by 1 minus r. or you could also write this as Sn is equal to a multiplied by r to the power n minus 1 divided by r minus 1. Hence what we obtained here is the sum of first n terms of a geometric progression. This is a small little trick to reach to this formula. So now if you have a geometric progression, you know the first term a, you know the common ratio r, and you know the number of terms n, then you can simply plug in the values into this formula and you can obtain the sum of first n terms of a geometric progression. One little thing to note here is the case when r is equal to 1. So what happens when r is equal to 1? It is just you are writing a plus a plus a plus a, so on up to n times. So this will simply be equal to n times a. So in case of r is equal to 1, all the terms are the same. So you are adding the same term n number of times, and the answer will be na, because if you try to plug in r is equal to 1 here, then it will be something divided by 0, which is not defined, doesn't make sense. So when in the case of r is equal to 1, it is simply you use your common sense, your general sense, which you should never lose in between all the formulas and everything. So you are just adding a n number of times and you get na, and this is the case when r is not equal to 1. Next we will try to solve some examples using the general formula of nth term and the sum of n terms of a geometric progression.